Okay, this is Mrs. Hall, and we are continuing in the Cognition Unit, Lecture 7, and we're dealing with problem solving, which means that we're looking at new situations that we've never encountered before, and we're trying to find a solution to this problem. A number of different strategies that we can use. The first one, very simply, trial and error. Just keep trying a lot of different solutions to this problem until you find one that actually works. Very time consuming, but it does work. In fact, Thomas Edison tried thousands of light bulb filaments before he actually stumbled upon the one that worked. And that was a simple trial and error. He just kept trying, and finally something worked. Don't ask me what that was. All I know is I can flip my light switch and the lights come on. Another problem-solving strategy that kind of goes along with trial and error is called insight. You probably remember this from your vocabulary terms. But this is a sudden, often it's a new realization of a solution, kind of like an aha, or a, oh my gosh, there it is, sort of a thing. It usually follows incorrect attempts at using trial and error. The answer just kind of comes to us after we've been puzzling over a problem for some time. It's also been described as being sort of a flash of inspiration. Sometimes, too, it's like a duh moment, but we call that insight. Thirdly, a math term for you here, algorithm. Using an algorithm to solve a problem is a very methodical, logical procedure that we use, and no matter what, no matter how long it takes, it guarantees finding a solution. Now, it takes a lot of time to do this because you're going step by step and you're trying every single possible alternative when trying to figure out the solution to a problem. For example, you take these letters here. You want to figure out what word this is. Now, some of you might have gotten it just like that when you see the word pop up, those letters pop up and you see the word. But if we wanted to use an algorithm for this, we're going to try each letter in each position until we solve the problem. That would take 907,208 possibilities in order to figure out that this word would be psychology. In math, you do this all the time. 10 times 2. Okay, I actually see my kids doing this sometimes when they're adding these numbers together, when they're trying to figure out their multiplication tables. 10 times 2 is 2 plus 2 plus 2 plus 2 plus 2. And it takes a long time. So algorithms, if you have to, but they're not the most effective way to solve a problem. Computers use algorithms, but they obviously can work a lot faster than we do. Finally, the last problem-solving strategy that I have for you is called heuristics. Now, heuristics are simple thinking strategies that allow us to make judgments and to solve problems more efficiently than using an algorithm. They're more error-prone than algorithms are, but they do provide a shortcut. So when you think of a heuristic, you want to think a mental shortcut. So some different ways that you can do this. You can work backwards if you want to. Sometimes in math, I know that the teachers will give you the answer to a problem, and then you can kind of figure it out by working backwards to see how to solve it. You can form sub-goals, break down large, complex problems into a series of steps and things, sub-goals that you want to solve as you come to the completion of the big problem. You can also use analogies, use a solution that you've had to a previous problem to solve a current problem that you're working with. Finally, you can change the representation of a problem. Instead of, having everything listed out in words, think of like story problems. Turn that story problem into a diagram or a flow chart or a graph or something like that, and have it look different than what the problem looks like right now. Not always the easiest to do, but it can be done. Another example of a heuristic would be, again, with these letters all put together here, you could find a shortcut by rearranging the letters and exclude certain letter combinations that we know won't work together. For example, in the English language, there are no words in the English language that have two Y's together. So you could cut that part of the step-by-step solution in the algorithm. You could use that shortcut, that heuristic there. Some obstacles to problem solving. We do run into these obstacles. First of all, it's difficult to think, I know. It's hard to think about what could the answer to this problem be and that sort of thing. But the first one is called confirmation bias. We're going to see this again when we get to social psychology, but confirmation bias is our tendency to look for information that confirms, obviously, that proves our preconceptions. So we're reluctant to seek information that might disprove our beliefs. So instead of looking for answers that would be incorrect, we're always looking for the answer that we think is correct. Professor Peter Watson, I think he's from Oxford, I don't remember, but he's from a British university, and he gave his students, on the first day of class, he gave his students 3 numbers on the board, 2, 4, 6. And he asked the students to guess the rule that he used to devise the series, 2, 4, 6. He said to generate their own sets of 3 numbers, and then he would tell them whether or not those numbers would work, whether they fit with the rule. And so you'd have students who would turn in 8, 10, 12. Well, the answer is yes. So they'd say, well, it's all even numbers. No, that is not the rule. Try another one. So they've got 2, 4, 6 already, so then they would say 20, 22, 24. Yes, those work. Then the rule is that they have to be ascending, even numbers. You add 2 to each number. No, that's not the answer. What students wouldn't do is they wouldn't do anything that contradicted that 2, 4, 6 in the beginning. So for example, to say 2, 4, 6 and then 8, 12, 15, okay? And when you say that, the answer is yes, that works, that fits the rule. Okay, well, now that kind of screws me up. Well, let me try something else. How about 15, 14, 13? No, that does not fit the rule. Well, as soon as you learn that no, it really helps you to figure out what the solution to the problem is. The rule really is any number that's higher than the number before it. So 2, 4, 6, any number that's higher than 6 could be the next number. And then whatever you pick after that has to be higher. Just consecutive higher numbers. Okay, not consecutive necessarily, but they just have to keep going up. You can't go down. Doesn't matter if they're odd or even. So just an interesting example. Sorry it took so long to explain it, but it will help you if you can find a no to a question when you're trying to find the solution to a problem. Fixation is another obstacle. Now, we saw fixation when we talked about Freud. With Freud, it was the fixation we became set back in one of our developmental stages. In problem solving, it's similar. We're set back from finding the solution to a problem because we can't see it from a fresh perspective. A couple of things that go along with fixation would be mental set and functional fixedness. Before we get there, I want to show you, I'll come back to this slide, but I want to show you an example. OTTF. What would the next 3 letters in that series be? Well, I'm going to tell you that the next series, or the next 3 letters would be F, S, S. Can you figure it out? We've got 1, 2, 3, 4, 5, 6, 7. It's the first letter of all the numbers starting with 1. So if we were doing this in class, it would be a little different. I'd have you work on that and try to guess it together. Got another one that's a little bit easier for you maybe. J, F, M, A, M, J, J. Did you figure it out? It's the months of the year. So our inability to see a problem from a fresh perspective can get us stuck. That we're looking for patterns and things when there might not be the same kind of pattern that you're looking for that's there. So let me go back up. Mental set, the tendency to approach a problem in a particular way, especially if that way has worked for us in the past. This may or may not be helpful in solving a new problem. We use the term perceptual set back in the sensation and perception unit. That type of a set predisposes what we perceive. We're going to perceive something that we've experienced before and we think that that's what it's going to be again. Mental set predisposes how we think. So we've had something work in the past before and we're going to think in the same way. In your textbook, page 317, figure 8-9, you can look at the jug problem on there and apply that to mental set. Functional fixedness. This is the tendency to think of things only in terms of their usual functions. We perceive the functions of objects as fixed and unchanging. We don't think outside the box all the time. We're looking all over for a screwdriver to, I've done this before, for my kids, to get the batteries out. And so I'm looking all over the house for a screwdriver when all I really needed was a dime. The dime would have unscrewed it, or a knife, a butter knife would have unscrewed it. In your textbook again, page 315, figure 8-6, you've got the string problem. And there's also in your book the candle mounting problem, where you've got a candle, 4 thumbtacks, and a box of matches, and you have to find a way to mount the candle on a bulletin board. Well, Functional fixedness is what prevents us from finding the solution to that problem. Look in your book and see the solution to that problem. All right, finally, a couple more obstacles. Irrelevant information. It leads us astray. I see this again with my kids. I know elementary teachers have to deal with this a lot with story problems, that they'll put extra information into a story problem to kind of throw you off. You don't really need all that information. All you need is maybe 2 sentences of the problem. So they put that in there to try to lead us astray, to see, can we weed through the information that is given to us and figure out the solution to the problem. And the last one is unnecessary constraints. Sometimes we will actually specify constraints on a problem without assuming that maybe there aren't any constraints that actually exist. The best example would be the 9-dot problem. This is from your textbook again, on page 317. Without lifting your pencil, draw 4 straight lines that cross through all 9 dots. If you want to try this, stop the recording right now and work on it and see if you can figure it out, and then turn it back on and I'll show you the solutions. There are 2 different solutions to this problem. Here's the first one, and here's the second one. And with the second one, it's even tougher because the lines don't go through the middle of the circles like we would expect them to. In this one, they all go through the middle. This one's even more outside the box. So that would be unnecessary constraints. So you've got your problem-solving terminology here, the big ones that you want to know: algorithm, heuristic, confirmation bias, fixation, mental set, and functional fixedness. Those are your big terms for this lesson. All right, I will see you soon.